Hello, everyone, and welcome to Lecture 12 of GPU computing. Today, we're going to talk about a different parallel scan algorithm than the one we talked about last time. In particular, we'll be talking about the Brent-Kung parallel algorithm for scan. So last time, we spoke about the scan pattern, and in particular, we looked at the Koji-Stone method for doing parallel scan. And we also looked at an optimization was applied in this context, but it's also applicable in many other contexts, and that is double buffering. So we said that scan is basically a pattern where, given an array, the output array is going to every element in the output array is going to be the combination of the preceding elements, as well as, if it's an inclusive scan, the corresponding element. If it's an exclusive scan, it's just the preceding elements without the corresponding element. And we were using addition as an example throughout the lecture, but we said that in general, scan can be applicable to other associative operators like product, minimum, maximum, etc. We said that to do scan, we segment it, like we did with reduction, and that's because doing scan in parallel requires synchronization, which we cannot do across different thread blocks. So what happens is that we take the input, we divide it into segments. Each thread block does a scan of its own segment, and then they store the partial sums in some array, and then we scan the partial sums array, and then we take the scanned partial sums, and then we go back, and each block adds the scanned partial sum of the blocks that precede it to it's the elements inside of the thread block to get finally the fully scanned global array. And the algorithm we looked at for doing a scan within a single block was the Koji-Stone parallel algorithm, which looked like this. What we did is we had each thread add the element that is one stride away, and then add the elements that's stride 2 away, then add the elements that's stride 4 away until we've reached the whole array that the thread block is responsible for. And we said that because we have this situation, which we did not have in reduction, by the way, but here we had a situation where on the same iteration, one thread was reading a value that was reading from a location that another thread was writing to. What happened is we had to synchronize between the read and the write. So we would read from this array, synchronize, write to the array, and then synchronize again. We also saw that these memory locations are being reused. So what we did is we loaded the data initially to shared memory and then performed our scan operation inside of shared memory. And then we also saw that well, the reason that we had to do a synchronization between reads and writes is because we were using the same array for each iteration. So to avoid this having to do two synchronizations every iteration instead of one, we instead used an approach called double buffering, where the threads don't read and write to the same buffer every iteration. Instead, we have an input buffer and an output buffer, and we read from the input buffer and write to the output buffer, and we swap input buffers and output buffers every iteration. That way, we only need to have two buffers. We don't need to have a buffer for every single iteration. And this optimization was called double buffering. Then we looked at exclusive scan, and we said that for the Koji-Stone approach, we can simply do an exclusive scan using the inclusive scan, but shifting the elements of the array by one element. And we finally analyzed the work efficiency of the algorithm, and we observed that although the sequential approach to doing scan performs n additions, the Koji-Stone approach took log n steps. Every step it did n minus 2 to the power step operations. So that came out to n times log n minus 1 operations, which is O of n log n operations. And with this observation, we said that this algorithm is not work efficient because the parallel algorithm does more work than the sequential algorithm. It does more additions than a sequential algorithm, which means that there is some redundant work that this algorithm is doing that the sequential algorithm does not do. Now, if the work is being done in parallel, that's a great idea. That's fine. It's a price that we pay. But if the thread blocks end up getting serialized because of limited resources, then we can expect this low work efficiency to hurt us. Okay, and with ending at that note, we said that today what we want to do is we want to talk about a different scan algorithm, which is the Brent-Kung method for doing scan. And then also we didn't look at coarsening last time, and we will look at coarsening today in the context of scan to see how coarsening would be useful for scan. So this is what we'll talk about today. But before I continue today's material, anybody have any questions about last time's material? Is everything clear to everyone? Okay, so then today we'll be talking about the Brent-Kung method for parallel scan. So the Brent-Kung method for a parallel inclusive scan, well, I'll start with inclusive scan, is as follows. We have an array, and what we do is this method has two steps. The first step resembles a reduction tree. So here what we will do in the first step is we will add the elements that are next to each other. So you'll notice here that these two elements now are ready. Okay, and the next step, we're going to add the elements. So here we have, oh yeah, and one thing to point out is that we're going to have one thread for every other element. Okay, so in Cogestone, we need to have one thread for every element. Here we have one thread for every two elements at the beginning, because the additions that we're doing in each step are fewer. Okay. So here we have a thread that adds every two adjacent elements, and then we continue. The next we have a thread adds these two elements that are two strides apart, and these two elements that are two strides apart. And over here, you'll notice that we have a complete reduction tree for this subsegment over here from 0 to 3. So now we have this value is ready. And then we're going to add the elements that are stride 4 apart. Okay, and you'll notice that now we have a complete reduction tree for the entire array. So now we have this value ready as well. So we essentially have done a reduction tree. Okay, and in the intermediate results of the reduction tree, we have some of the scan values are ready, but some values are not. Okay, and because this looks like a reduction tree, we call this the reduction step. Okay, we call this the reduction step. Now, after doing this, we still have these other values that are not ready yet. So what we're going to do is we're going to do a second phase where we complete these other values that are not ready. So for example, we observe here that x4, x5 is not ready. It's missing x0 to x3. Well, we have x0 to x3 over here. So in this stage, so we had stride 1, stride 2, stride 4. Now we're going to go back to stride 2, and we're going to add x0 to x3 with x4 to x5 in order for us to get x0 to x5. And now this value is ready. But what we noticed is that we still have x2, x4, and x6 are not ready. But here x2 can be added to x0 and x1 so that we get x0 to x2. x4 can be added to x0 to x3 so that we get x0 to x4. And then x6 can be added to x0 and x5 so that we get x0 to x6. So essentially what we do is we simply add the values that are one stride to the left in order for us to complete the scan array. Okay. And this step, following the reduction step that we use to complete the remaining values, is called the post-reduction step. Okay? Is it clear to everyone how this works? Okay, so then now let's compare these two methods. So here on the left, we have the Cogestone method that we saw before. And here on the right, we have the Brent-Kung method that we looked at now. And what do you notice about the similarities and differences between these two methods? Well, differences. What's different? What are the differences between these two methods?
Have fewer additions total, right?
For which one? Which one has fewer additions?
For the Brent-Kung.
Right. So the Brent-Kung approach has fewer additions in total. Okay. Somebody is saying depth. What do you mean by depth?
The Brent-Kung goes deeper into the tree.
I think like it means more steps.
Right, exactly. So the Brent-Kung has more steps. So the Brent-Kung approach that performs more steps. However, it performs fewer operations per step and fewer operations in total. Okay, and let's kind of do an analysis of these two approaches. So if you remember, when we talked about work efficiency, we concluded that the Koji Stone approach has log n steps. However, it does O of n log n operations. Now let's do an analysis of Brent-Kung. So Brent-Kung does how many steps? Well, let's take a look. There's two different stages. There is the well, let me go back. There's the reduction step and there's the post-reduction step. And the reduction step, how many steps do we do? Well, here I have 8 elements. I did 1, 2, 3 steps. So in general, if I have n elements, I do log n steps. Okay. And then in the post-reduction step, here I went 1, 2, 4, and then I go back. I go back and I do 2 and then 1. So how many steps do I do in the post-reduction step?
Log n minus 1, or roughly log
Right,
n.
exactly. Log n minus 1. So in total, we're going to have 2 log n minus 1 steps. So that's more steps than Koji Stone, which finished in log n. However, how many operations do we do in each step? Here, when we have 8 elements, we did 4, and then 2, and then 1. So that's 7. So that's around log n operations. And then we go back and we do 1, and then 3. Okay, if you have another iteration, we're going to do more than that. So let's go and do the full analysis. So with Brent-Kung, we said the reduction step does log n steps, and it does 1 plus 2 plus 4 up until n minus 2, which is equal to n minus 1 operations. Okay, and maybe I should have written this as n over 2 plus n over 4 plus dot 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 plus 1, because the first step does n over 2, the second step does n over 4, and then the very last step does 1 operation in the reduction step. Okay, for the post-reduction step, we said that we have log n minus 1 steps. Okay, and then in the first step, we did one operation, that's 2 minus 1. In the second step, we did 3 operations, that's 4 minus 1. And in general, we're going to keep going until we get to n over 2 minus 1. So we'll do 2 minus 1, 4 minus 1, 8 minus 1, 16 minus 1, until we get to n over 2 minus 1. So if you add this up, this comes out to n minus 2 minus log n minus 1, right? Because we have 2 plus 4 until you get to n over 2. That adds up to n minus 2, okay? And then you have 1 plus 1 plus 1 log n minus 1 times, so that's log n minus 1, okay? So if you add the steps and the operations for the reduction step and the post-reduction step, in total, we find that the Brent-Kung approach takes 2 log n minus 1 steps. So that's more steps than the Koji Stone approach, okay? However, it does, if we add, n minus 1 and n minus 2 minus log n minus 1, it comes out to 2 times n minus log n minus 2, which is O of n operation. Okay, so that the Brent-Kung approach does fewer operations. Okay, so Brent-Kung takes more steps, but it is more work efficient. Is that clear to everyone? Okay, so then let's go and implement the Brent-Kung approach. But before that, in the past lectures, we've been kind of implementing something and then gradually optimizing it. What I'm going to do is I'm just going to implement the optimized version in one step just to save time today, because doing the optimizations incrementally is something we already did in the last lecture for Koji Stone. So what optimizations are we going to apply to the Brent-Kung approach? The optimizations we applied last time were that we used shared memory, we did double buffering, and well, we didn't have a problem with divergence. But what we're going to do today is we're also going to use shared memory, so similar to Koji Stone. Okay, and this should be obvious. However, there's one thing to note when we compare the use of shared memory for Kojistone versus Brent-Kung. So in both cases, we're reusing the same memory locations, so using shared memory is useful. However, with the Kojistone approach, when we use global memory, the memory accesses were actually coalesced. Okay, now when we use shared memory, it wasn't a problem. Coalescing was not a problem. But in the Brent-Kung approach, if we use global memory, the accesses are actually not coalesced. So using shared memory has two advantages with the Brent-Kung approach. The first advantage is that we get data reuse, so we don't have to go to global memory every time. But then the second advantage is the fact that we get better behavior because we can load the whole array in a coalesced way, and then we continue with these non-coalesced accesses. Okay, so those are the two advantages. So using shared memory is similar to Kojistone. We get better data reuse, but it also enables coalescing of global memory loads. In Kojistone, the global memory loads were already coalesced before we applied shared memory tiling. Do we need to do double buffering in Brent-Kung? So in Kojistone, we had to do double buffering. Do we need double buffering in the Brent-Kung approach?
No.
Why not?
Because we don't access the same areas we are writing to.
Right, exactly. So the reason we needed double buffering with Kojistone is that on the same iteration, X1, for example, was being read by one thread and it was being written by another thread. So we needed to make sure that the thread that is writing doesn't interfere with the thread that is reading. And that's why we wanted to read from a buffer and write to a different buffer. In Brent-Kung, it is never the case that the same value is being written by one thread and read by another thread on the same iteration. So we don't need to worry about double buffering. We can use a single buffer for all our steps. Okay. So then we no need for double buffering because unlike Kojistone, no data element is read and written by different threads on the same iteration. The one thing though that we need to be careful about with the Kojistone approach is, the Brent-Kung approach is control divergence. So with Kojistone, the control divergence was not a problem, right? Because in the first step, all the threads were active except maybe the first one, right? But that's okay. The threads that were active were all next to each other. So threads 1 to 7 were active. In the second step, threads 2 to 7 were active. In the third step, threads 4 to 7 were active. But the point is that the threads that were active in each step were all next to each other. Whereas in the Brent-Kung approach, if we assign a thread to every input value, if a thread owns an input value, then we would have a problem with control divergence, and that is that because we don't process all the input values at every step. These input values drop out. So if I'm going to assign a thread to every input value, then at the first iteration, I'm going to have 1, 2, 3, 4 all busy. The second iteration, every other thread drops out. In the third iteration, every other thread drops out, etc. Okay. So to avoid, we need to minimize control divergence. And to avoid this control divergence, what we're going to do is that we are not going to assign threads to specific data elements like we did with the Kojistone approach. Instead, what we will do, so we're not going to do what we've been doing so far with these tree reductions and scans, where every thread owns a particular element in memory. Instead, what we're going to do is we're going to use a different approach, and that approach is to re-index the threads every iteration to different data elements. Okay. In other words, at every iteration, right, the thread is going to be responsible for a different data element, so that I can always have threads that are next to each other active, and threads that are the threads that are farther away inactive. So, for example, what I would like to do over here is on the first iteration, okay, I'm going to have thread 0 do this addition, thread 1 do this addition, thread 2 do this addition, thread 3 do this addition, etc. On the second iteration, I'm not going to have threads. So first I had 0, 1, 2, 3, etc. I'm not going to have thread 0 inactive and then thread 1 do this, and then thread 2 inactive and then thread 3 do this, and then thread 4 inactive and then thread 5 do this, etc. I'm not going to do that. Instead, I'm going to reindex my threads to be responsible for different data elements in each iteration. So what I will do is I will have thread 0 process this element, thread 1 process this element, thread 2 perform this addition, and thread 3 perform this addition. And then on the third step, I will have thread 0 perform this addition, and thread 1 perform this addition. And then on the final step, I will have thread 0 perform this addition. And then the same thing as I go back out, I'm going to have thread 0 perform this addition, thread 0, 1, and 2 perform these, and then thread 0, 1, 2, 3, 4, 5, 6 perform these. So we always want to assign the leftmost addition to the first thread, and so on, regardless of what element that is. And what that means is that each thread will be responsible for a different input element in each of these iterations. Okay, is that clear?
Doctor, but why do we need the threads to be contiguous, like next to each other? Is it because to maximize the warp usage? If we have more than one warp and we want them to be as packed as possible?
Right, exactly. So what I want to do is I want to fill up the first warp before I fill up the second warp, etc. I don't want to have every other thread in the block active or inactive, because then I'm going to have a lot of control divergence. Okay, so what I'm trying to do is to minimize control divergence by always assigning the work to the thread starting from the left. So I fill up here maybe it's not obvious because I just have 16 elements, but this could be 1,024 elements. So if this was 1,020, or it could be 2,048 elements, and I could have 1,024 threads. Okay, so I want to fill up the initial warps before I fill up the later warps. Okay, is that clear?
Yes, thank you.
Okay, so then to do this, we need to be able to play some tricks with the thread indexing, and to figure out how we're going to index the threads. So every iteration, the thread, the element that the thread is going to be responsible for is now not the same for all iterations. It's going to be a combination of the thread index as well as the iteration. And the iteration was represented with the stride. We used the stride somehow as our loop index that was doing the iterations. So what we will do is we want to express the index, the element that the thread is responsible for in terms of the thread index, which I will denote as T, and the stride, which I will denote as S. So if you notice in the first iteration, if we look at the index of the right source element, and the destination element of the thread, okay, these are the indices. Okay, so in the first, when the stride is 1, thread 0 needs to be responsible for element 1, thread 1 for element 3, thread 2 for element 5, thread 3 for element 7, etc. So here I have 1, 3, 5, 7. When the stride is 2, my threads are responsible for element 3, element 7, element 11, and element 15. So I have 3, 7, 11, 15. So so thread 0 is responsible for element 3. Thread 1 should be responsible for element 7. Thread 2 is responsible for element 11, etc. When my stride is 4, then here the first thread, so thread 0 should be responsible for element 7, and thread 1 should be responsible for element 15. So here, when my stride is 4, thread 0 is responsible for element 7, and thread 1 is responsible for element 15. And then when my stride is 8, then over here, only thread 0 is going to be active, and thread 0 is going to be responsible for element 15. So here I'm going to have 15. Okay? So this is for the reduction step. In the post-reduction step, now let's figure out the indexing in the post-reduction step. And here I'm going to look at, in the reduction step, I was looking at the right element that the thread is responsible for. And the post-reduction step, I'm going to look at the left element that the thread is responsible for. So here in the post-reduction step, when the stride is 4, I'm going to have thread 0 responsible for element 7. Okay. When the stride is 2, I'm going to have thread 0 responsible for element 3, thread 1 responsible for element 7, and thread 2 responsible for element 11. Okay, and etc. Here I'm going to have 7, Here I'm going to have 3, 7, 11. Notice how these resemble these up here. So when stride is 2, in both cases it's the same. And then when the stride is 1, I'm going to have 1, 3, 7, 1, 3, 5, and 7. Okay. The reason I'm doing this is I'm just trying to figure out some closed form representation of the element that the thread is responsible for in terms of the thread index and the stride. Okay, so this is for each value of the stride and for each thread what element they are responsible for each stride value. Okay, so now the question is, how can I represent the index of the element that a thread is responsible for in terms of the stride value and the thread index? Okay. Well, what we observe here is that over here, the thread elements are 2 apart, right? So +2, +2, +2. Here they're 4 apart. Here they're 8 apart. Here I just have 15. When I come back here, they're 4 apart again. Here they're 2 apart. So in general, they are 2 times s apart. Okay, but they're an odd number, not an even number. Okay, so what I will do is I will represent them as something -1. So here 1, I will represent it as 2 minus 1. I will represent 3 as 4 minus 1. So I will just represent everything as something -1. Okay, and now it becomes more apparent that these are all a multiple of 2 times the stride, right? So here, when the stride is 1, 2, 4, 6, and 8 are all multiples of 2. When the stride of 2 is 2, then 4, 8, 12, and 16 are all multiples of 4. When the stride is 4, then 8 and 16 are multiples of 8. So in general, the thread indices are a multiple of 2 times the stride. So I can represent them that way. I'm going to represent the indices as multiples of 2 times the stride. Okay, so here, now each index is, here it's 1 times 2 times the stride -1, 2 times 2 times the stride -1, etc. Here it's 1 times 2 times the stride -1, 2 times 2 times the stride -1, etc. And what you'll notice is that these remaining numbers in black, these are just the thread index +1. Okay, so when the thread 0 is always going to be responsible for 1 times the element at index 1 times 2 times s -1. Thread 1 is always going to be responsible for the element at index 2 times 2 times s -1, and etc. So this is simply going to be so the indexes are the t plus 1th multiple of 2 times s, and then of course -1. So we just replace this with 2 minus 1. And this over here, t plus 1 times 2 times s -1, gives me the index of the element that each thread is responsible for each stride value. Okay, is it clear? So figuring out this indexing, remember when I told you guys that parallel computing is all about indexing and boundary checks? Well, figuring out this indexing is the hardest part of writing this kernel. Okay, once we have this expression for the index, everything else is fairly easy, as you will see. All right, so every thread is going to process the t plus 1 times 2 times s -1 element, of course, if the destination is in bounds, right? So over here, we will need to check if the values are in bounds. In this situation, this equation will take thread 0 here, but I'll take thread 1 somewhere all the way out here, which is out of bounds. So I simply don't process. That's how I know that in this for this stride value, thread 1 is not going to do anything. Okay?
Professor?
Is this clear? Any questions?
Yeah, Professor, I was just confused in the post-reduction step. Why was there, I thought it was supposed to be 11 when the stride was 4, but there was another value. I think there was 7.
Okay, yeah. So what I wanted to do is I wanted to have the same index for stride 4 here and here. And that is why what we did is for stride 4, the first thread was the index that we used was the index of the right operand and the destination, where in the reduction step. But in the post-reduction step, the index that we use is the index of the left operand. And what this allowed us to do is it allowed us for stride 4 that thread 0 had the same index in both reduction and post-reduction.
Oh, I see. Okay. Okay.
Yeah.
Thank you.
And you'll notice here, the left, when stride is 2, the left operand, the right operands are 3, 7, 11, and 15. Okay, and then when stride is 2 down here, the left operands are 3, 7, 11, and of course for 15 it will be out of bounds, so there's no 15. Okay, so using the right operand as the index in the reduction step and the left operand as the index in the post-reduction step allows us to have the same index in both cases.
I see. Okay,
Doctor?
thank you very much.
Yeah, you're welcome.
Doctor,
Okay, so this is
I have a question.
this is an example of how we can re-index the threads. So rather than assigning threads to fixed data, we re-index the threads every time in order for us to make sure that we do not have control divergence. And this idea of re-indexing threads is a general approach to avoiding control divergence that we apply every time. Here we are applying it in this context, but in other workloads we might apply it in a different context. Does someone have a question?
Please. So best this trick that we use, the right indexing versus left indexing, it's something we have to try always. And if I have a new algorithm that I don't know the parallel, I don't know its parallel pattern, I have to try different things, right? There is no like fixed way to
Right. Yeah.
right, left.
Yes, you're right. So different algorithms. Yes. So this here is something that's specific to what we're working on today. You're absolutely right. What I'm saying is the general idea of re-indexing threads as opposed to fixing the threads to specific data and letting them diverge is what we're trying to showcase here.
Okay, thank you.
Okay, yeah, you're welcome. All right. Well, having explained this, let's go and implement this Brent-Kung approach for parallel scan. Okay, so this here I've set up the code already. This code is quite similar to the code that we wrote last time. We have this the host code that is calling a scan kernel. And then we have this recursive step that scans the partial sums, and then there's an add kernel that adds the final result. Okay, and the add kernel is already implemented. We just need to implement the scan kernel based on what we saw today. So let's begin to implement the scan kernel. So the first step is I want to find the segment in the input that the thread block is responsible for. Now, one distinction between Cogistone and Brent-Kung is that in Cogistone, so let me go back. In Cogistone, I had as many threads as I had input elements. And the reason was that I needed that many threads because I was doing an operation for every input element in the first step. Whereas in Brent-Kung, I need half as many threads as I have input elements. Okay? So the size of my input is going to be twice my block dimension. All right? That's one thing to keep in mind. Okay, so here the size of my input, the number of threads that I need is half the size of my input. So every thread block is going to take a segment that is twice the block size. Okay, so in other words, I'm going to start by finding the segment of the thread block, and the segment of this thread block is basically going to be blockindex.x times blockdim.x times 2, because I have twice as many input elements as I have threads. Okay. Now the next thing to do, remember we said we're just going to do all the optimizations together. So what we want to do is we're going to load this input array from global memory to shared memory. So I'm going to create a shared memory array. I'm just going to call it buffer underscore s. Okay, and what's the size of this shared memory array going to be? If this is my block dim, then what's the size of the shared memory array going to be?
Block dim.
Is it going to be block dim only?
It's twice.
Block them times 2.
Right, it's going to be block dim times 2, because again, I have twice as many elements as I have threads. Okay, now since the size is block dim times 2, I'm going to need every thread to load 2 elements, and to do this in a coalesced way, I'm going to have all my threads load the first half of the segment, and then all the threads load the second half of the segment. Okay, so I will do buffer underscore s of thread index.x is equal to input of segment plus thread index.x. So here segment is the index of the very first element in the segment that the block owns, and then each thread is going to load one element starting from the beginning of the segment. Okay, and then in the next step, each thread is going to load a second element, which is going to be the top half of the segment that the block is supposed to compute with. So here it's going to be thread index.x plus, let's go plus segment, thread index.x plus block dim, and thread index.x plus block dim over here. Okay, and then of course I need to sync threads to make sure that I've read all the values from global memory before I start doing my tree. Okay, clear to everyone? Okay, now that I have my data in shared memory, so now this array is in shared memory. The next step is for me to do this tree, and what I will do is I'll first start with the reduction step. Okay, I'm first going to start with the reduction step. So let's write the loop that iterates through the reduction step. Initially, my stride is 1, and then it's 2, and then it's 4, and then it's 8. Okay, and it stops at 8. What is 8? 8 is half the size of the input. The input is 2 times the block dimension. So 2 times the block dimension over 2 is simply the block dimension. Okay, so my loop is going to start at stride equals 1, and it's going to keep going until stride is equal to block dim. So stride less than or equal to block dim. Okay, where did I get block dim? Again, the size of my input array is 2 times block dim, and the largest stride is going to be half the size of the array. So half of 2 times block dim is block dim. Where stride equals 1, stride is less than or equal to block dim, and then every iteration I'm going to multiply stride by 2. Okay, and then on each step, what am I going to do? I'm going to add. I'm going to first. I want to figure out. So this is where the indexing comes in. I want to figure out what element my thread is responsible for. Okay, and the way I figured out is using this equation. This equation, t plus 1 times 2 times s minus 1. Okay, so I'm unsigned int I is equal to thread x plus 1 times 2 times stride minus 1. Okay, so now every thread knows what it's responsible for. Now each thread is going to add the elements it's responsible for to the element that is stride to the left. Okay, so I'm going to write buffer underscore s of I plus equals. So each thread will add the element it's responsible for to the element that is stride to the left. So it's going to add it to buffer underscore s of I minus stride. Okay. And of course, I need to make sure that the element that I'm responsible for is actually within bounds, right? So I don't want the thread on this iteration. I want some threads are going to be all the way out here. I only want threads 0 and 1 operating over here. Thread 2 is going to be somewhere all the way out here, and that's going to be out of bounds. So I don't want thread 2 to do anything. So to do that, I'm going to make sure that I, the element I'm responsible for, is actually within bounds. What is the bounds here? What is the size of this array? It's 2 times block dim. Okay, it's 2 times block dim. Right, and you can easily see how this works, right? Because here buffer underscore s, the size of buffer underscore s is 2 times block dim. So obviously, when I access buffer underscore s of I want I to be less than 2 times block dim. So this is kind of another example of how these boundary checks always correspond to some memory location that I'm accessing, and I want to make sure my access is within bounds. Okay. All right, so after I do this addition on each iteration, I'm going to sync threads. Okay, and then when this loop is over, I'm done with my reduction step. So next, what I need to do is I need to do my post reduction step. Okay, so with my post reduction step, my stride is gonna start at in this case 4. Okay, so in general, okay, if I want to write the loop bounds for the post-reduction step, I'm gonna do unsigned and stride is equal to, what is the first value of stride in the post-reduction step? Where did I get 4 from? Well, it is half of the stride at the end of the reduction step. The stride at the end of the step is block dim. Okay, so then the stride at the beginning of the post-reduction step is going to be block dim over 2. Okay, is that clear to everyone? Where I got block dim over 2 from? Okay, and then I'm going to keep going until 4, 2, 1. So I'm going to keep going until the stride is 1. So 4 stride equals block dim over 2. Stride is greater than or equal to 1. Okay, and then I'm going to divide stride by 2 every iteration. Okay, so I'm going to do stride divide by 2. Okay, now what do I do? Well, again, figure out what element the thread is responsible for. And fortunately, we were able to cleverly use the same index for the reduction step and the post-reduction step. So I'm simply just going to copy the index that I used up here. So thread index.x plus 1 times 2 times stride minus 1. Okay. However, this time what's going to happen is every thread is going to remember this index is the index for the left element. So every thread is going to add this element to the element that is stride to the right and store the result in the element that is stride to the right. Okay, so I'm going to increment the element that is stride to the right by the element that I'm responsible for. Okay, so I'm going to do buffer underscore s of I plus stride plus equals buffer underscore s of I. Okay, so I take the element on the right and I increment it by the element that I'm responsible for. Okay, if I'm responsible for this element, then I take the element that's stride to my right and I add to it the element that I'm responsible for. Okay, and of course I need to have a boundary check over here. Okay, so basically I need to check that not only should my element be in bounds, but the element to my right should also be within bounds. Okay. So here I need to make sure that I plus stride is less than, what is the bounds? What is the bounds of the array?
Blocked in.
Times blocked in. Okay, it's 2 times blocked in. So 2 times, oops, it's 2 times blocked in. Okay. So the previous tree, I had to make sure that I was less than 2 times blocked in. In this tree, I have to make sure that I plus stride is less than 2 times blocked in. Okay, and then I will synchronize. And by that, I'm done with the post-reduction step. Now, once I finish the post-reduction step, what are the final things I need to do? Well, I need to update my partial sum. So the partial sum is going to be the value of in the very last element of the buffer. So I'm going to have one thread be responsible for updating the partial sum. It can be any thread. Okay, I'm just going to use thread 0. So if thread x equals 0, then the partial sum of the block, so partial sums of block index.x, the partial sum of the block is going to be equal to the value at the very end of the buffer. So buffer underscore s of how big is the buffer? It's 2 times block dim. So what is the index of the last element in the buffer? It's 2 times block dim minus 1. Okay, so this way I've updated the partial sum, and this will be used later on to scan the partial sums and then go back and do the addition. Okay, and then finally, what I need to do is I need to store my output value. And just like each thread is responsible for loading 2 input values, each thread is going to be responsible for storing 2 output values. Okay, so I will index the output. The beginning of my the segment tells me the beginning of my input segment, and therefore it also tells me the beginning of my output segment. So here I'm going to have output of segment plus thread index.x is equal to buffer underscore s of thread index.x. Okay, and of course I also want to add the element so what this does is it's going to store to the output the first half of the result array. I also want to store the second half of the result array. So to do that, I'm going to also have this, but then I'm also going to add at the end here blocked in. Okay, so segment plus thread index.x plus blocked in, and I will add I will store there buffer of thread index.x plus blocked in. Okay. Now, of course, here when I access the input and when I access the output, I need to make sure that these indices are within bounds. Okay, so I will need to use n to make sure that these indices are within bounds. And I'm not doing that intentionally in the lectures. I'm not worrying about boundary check. I'm assuming that n is evenly divisible by 2 times blocked in. But in practice, this might not be the case. So in the assignment, when you solve a similar when you write similar code, you're going to have to make sure that you handle the case where n is not evenly divisible by 2 times blocked in, and make sure that when you access the input here and that when you access the output here, that you perform the right boundary check. Okay, so this is the code for the Brent-Kung scan. Any questions about it before I run it?
Yes, can you repeat just the last 2 lines what we did?
Okay, so what we did is we loaded at the beginning up here, we loaded the input segments to shared memory, and then we did our scan in shared memory, and now we have our result in shared memory. So we want to store our scanned result to global memory. Okay, so here but when we're done with the reduction step and the post-reduction step, my result is still in shared memory. And I will store that to the output, which is global memory. So here, that's what I did. Okay, clear?
Yeah. Okay. Yeah, but we did twice because we have two blocks. And we did
sorry.
We did it twice, and once for segment plus thread index.
So the reason we did it twice is because the thread block is responsible for twice as many elements as the number of threads that it has.
Okay, thank you.
So that is why when we loaded the input element, each thread had to load 2 input values, and when we stored the output elements, each thread has to store 2 output values. Okay. Otherwise, we would need to have threads that were only active when we are loading the input over here and then storing the output over here, which is a waste. Okay. Then let's compile this. Let's hope it runs correctly for the first time and we don't have to do any debugging. Okay, there we go. So the result is correct. And as you can see, the baseline code took 50 milliseconds, whereas in the CPU code, whereas on the GPU, it took around 6 milliseconds to perform the scan. Okay, now of course the total time is high because there's high overhead from doing the copy to and the copy back. However, in practice, if your data is already on the GPU, it's definitely worthwhile doing the scan on the GPU and not bringing the data to the CPU. Okay, so this is the code that we wrote. And if we want to do an exclusive scan, okay, there's 2 approaches to do the exclusive scan. We can do what we did with the Koji-Son approach, where we just formulate the exclusive scan as an inclusive scan by shifting the elements 1 input to the left. Okay, but there's also kind of another way to do the exclusive scan, and that is by using a different post-reduction step. Okay, let me show you what that looks like. So if we want, there's a kind of another way in the Brent-Kung approach to do the exclusive scan. The reduction step remains the same. So we do a reduction step just like with the inclusive scan. However, what changes is the post-reduction step. So when I want to do the exclusive scan, I can change the post-reduction step in order for me to achieve an exclusive scan, okay? And this is what I will do. The first thing I do is that I'm going to set aside this x0 to x7. This is going to be the sum of all the elements in my array. So I will need that because this is going to be the partial sum of the block, but it's not going to be part of the result in the actual array because this is an exclusive scan. Okay, so I will set aside x0 to x7. I will save it as the block's partial sum. Okay, but I will replace it with 0. And now, since this is exclusive scan, this 0 is misplaced. I'm supposed to have 0 in the very beginning, right? This x0 is misplaced. x0 is supposed to be here. This x0 to x1 is misplaced. It's supposed to be here. This x0 to x3 is misplaced. It's supposed to be here. So somehow I want to take the 0 back all the way here to its place. I want to take x0 to its place. I want to take x0 to x1 to its place. And also I want to complete these other values. Okay? And the way I will do it is as follows. In the first step, my stride is 4. And what I will do is I will move the 0 here. And I will add the 0 to x0 to x3 and put the result over here. Okay? I know this looks a little bit weird, but it'll make sense in a minute. Okay, what I'm doing is I want to move x0 to x3 over here eventually, but intermediately what I will do is I'm going to move it all the way here, and then later on I'm going to move it back. And I want to move this 0 all the way here eventually, but what I'm going to do is I'm actually going to move it only this far, and later on I'm going to move it back. Okay? So I moved the 0 here, and I moved x0 to x3 over here while adding it to 0. And the next step, what I want to do is I want to move this 0 closer to where it's supposed to be, which is here. And I want to move x0 to x3 closer to where it's supposed to be. Okay, so the next step, I will move the 0 over here, and I will move x0 to x3 over here. But I will also add 0 to x0 to x1 and put the result here. Okay, remember x0 to x1 needs to come here, but I will temporarily move it here. Okay, and here x4 to x5 still needs x0 to x3 so that I can get x0 to x5, and then I need to move it here eventually. But what I will do is I will add it to x0 to x3 and bring it here. Okay, and then later on I'm going to bring it back to where it's supposed to be, which is here. Okay, and you can probably now see more clearly where this is going. Okay, so here I have a stride of 4. And what I do is I move one of the elements and then I add another one of the elements. Okay. In the next step, I have a stride 2, and again I move one of the elements and then I add another one of the elements. Okay. And then the final step, I will do the same thing with stride equals 1, and voila, everything now works. I move 0 over here. I move x0 over here by adding it to x1. Here x2 was missing x0 to x1, so I added to x0 to x1 to get x0 to x2 over here, and I move x0 to x1 down here. Okay, same thing with over here, and same thing with over here. And this post-reduction step is indeed a clever way of achieving an exclusive scan without formulating it as an inclusive scan. Okay, is this clear to everyone? So here, this post-reduction step is exclusively for the exclusive scan. Any questions?
Professor, I'm struggling to see why we just don't do it the same way and then like keep the 0 at the end and then just send whatever, like send it all with like a delayed index of 1, like I minus 1
we
and
can,
0.
We can do it that way. Right? We can do it that way. So
but why is it not
like
faster?
there's 2 ways to do it. Okay.
But is it not
There's 2 ways
faster?
to do it. One way is to formulate it as an inclusive scan by shifting all the input elements. Okay. And another way is to use a different post-reduction step. Right? And both of these are valid ways of doing it, right? I just wanted to show you this way because it's a clever way of doing it, and it's kind of nice to observe how it works. Okay.
Okay.
And there's actually a second reason why I wanted to show you this approach. The reason I would like to show you this approach is because we're not going to implement this approach in class, that you will have to implement this approach for your assignment. Okay, so this is so another reason I'm showing you this is you'll implement this approach for your assignment. It is true that we could also use the inclusive formulation. However, this hopefully you will find this as an enjoyable exercise to practice reasoning about thread indices and how to pick the right indices and reindex the threads when you are implementing something like this. Okay.
Will we have to worry about the array not being a multiple of the number, like of the size of the block? So having
yes. So in the homework assignment, you will have two things to worry about that we didn't do in class. One of them is you will need to worry about the boundary checks when you read the input from global memory and store the output to global memory. And the other thing that you will have to do in the assignment is you will have to implement this post-reduction step for the exclusive scan as opposed to the post-reduction step for the inclusive scan that we did in class.
Okay, thank you.
Okay. Okay, so what do you guys think? Do you guys like this Brent-Kung approach for doing parallel scan? What do you guys like more, this approach or the Koji-Stone approach?
This is more convoluted, but it's nice.
Right, so this is I think the Koji-Stone was maybe a little simpler, but remember this is more work efficient, right? Remember the Koji-Stone approach was less work efficient. This approach is more work efficient, but it takes more steps.
But
Now,
Professor,
what has better performance, the Koji-Stone approach or this approach?
the Koji-Stone approach.
Why do you think the Koji-Stone approach does better?
I mean, my point of view is just if we're running it on a GPU, might as well parallelize it as much as possible and not have many steps. Like this is more sequential than the other one in some regard.
Okay, so this one takes more steps, but it does do less work, right?
Yeah,
So
but I mean, if we put
O
it
of
on
n work, Koji-Stone does O of n log n work. So let's go back. Remember the performance of our Koji-Stone approach. So here, remember, we got 6 milliseconds for the Brent-Kung inclusive scan. Let's go back.
0.4, I think. Like that.
Let's go back, and this is our code for Koji-Stone. So let's run it and see what the performance we had. And it was around 4 point something. Okay. So the lesson here is as much, work efficiency is very important, but we always have to, sometimes there's a trade-off that we have to make. Okay, let's see what's going on. So work efficiency, the reality, while the Brent-Kung approach has higher theoretical work efficiency than the Koji-Stone approach, in practice, its actual resource consumption on the GPU after accounting for the inactive threads is O of n log n. And what do I mean by that? If we go back to the comparison here, okay, it is true that the Koji-Stone approach does more work than the Brent-Kung approach. The Brent-Kung approach does less work. However, on many of the iterations that the Brent-Kung approach is doing less work, the work that I'm saving is being done by threads that are bound to these threads by SIMD anyways. Okay, so once I get to the point where I'm using a single warp, right? When I'm using multiple warps, fine, right? I'm saving a lot of work. But once I get to a point where I'm inside of a single warp, right? Using fewer threads, using 16 threads in the warp instead of using 32 threads in the warp. So having 16 threads do an addition in the warp instead of having 32 threads do an addition in the warp doesn't really benefit me. Because even if I've saved those threads from doing any work, they are still occupying resources because of the way that SIMD works. Okay? So in practice, it's actual resource consumption on GPUs after accounting for inactive threads. So if I consider the inactive threads that are occupying cores because they're bound by SIMD, it actually is more similar to n log n than it is similar to log n. So it is log n perhaps in the amount of real work that it does, but it is n log n, closer to n log n if you consider the inactive threads, the threads that are not doing work, but they are occupying cores because of SIMD. If you consider those to be doing work, then it would be closer to O of n log n. Okay, and that is why the performance of Brent-Kung on GPUs in particular, or in general if we have SIMD, is similar or sometimes maybe even worse than Koji Stone, as we saw. Okay, so it is still an interesting case study. We still showed you this Brent-Kung approach because we think it was an important case to study in order for us to learn about work efficiency and see the trade-off between work efficiency and parallelism. So sometimes it might be worth paying it might be worth performing more redundant work in order for us to be able to get more parallelism. Okay. Any questions? Somebody's saying if we're bound by SIMD, the inactive threads are actually performing the same computation as the active threads, but we're disregarding their result. What I mean is that if the inactive threads that are bound to the active threads by SIMD, if they performed computation or they didn't, it will not impact the performance. Okay, so had they been active and doing and performing actual computations, we would not have seen a performance difference because that work was completely hidden because they were bound by SIMD. That's,
okay, so so the power consumption, the dynamic power, the ALUs are still running and they're still performing the computation, but we're just not taking the result. And because they're bound by SIMD, it's not, they're still performing the instructions, right?
Right. I mean, it just depends how you want to think about SIMD. You can think about them as performing the instructions and not taking the result if you want.
Okay.
Okay. So having seen this, a final topic I'd like to talk about, since we've spoken about work efficiency, a final topic I want to talk about is thread coarsening. Okay, so remember we said that thread coarsening is an optimization that is useful whenever we have a certain price that we pay to parallelize something. Okay, and what is the price that we pay to parallelize scan? Well, similar to reduction, we have the synchronization overhead and we have the control divergence. Okay, well, there's another price that we pay to parallelize scan, particularly with Koji Stone. What is it?
Shared
you just
memory.
mentioned it on the previous slide.
Shared memory.
Well, that's not what I had in mind. What's the overhead of parallelizing scan?
The work, so you're doing more work, I guess.
Right, exactly, work efficiency. So parallelizing scan incurs the overhead of lowering the work efficiency of our algorithm. Okay, now, if all my thread locks are going to run in parallel, then that's great. Okay, I'm paying that price of low work efficiency in order for me to get parallelism. But if the resources are insufficient and the hardware will serialize these thread locks, then this lowering of the work efficiency that I'm paying is unnecessary. So what can we do in this case in order for us to reduce the loss in work efficiency that we're getting from over parallelizing the workload? Well, we can apply thread coarsening. Okay. And the way to apply thread coarsening in the context of a scan, one way to apply thread coarsening in the context of scan is using a segmented scan. And the way we do that is that every thread is going to scan one of a segment, is going to have its own segment. It's going to scan that segment sequentially. Okay. And remember, sequential scan is more work efficient than parallel scan. And then we're going to only have a parallel scan on the partial sums of each thread. Okay. So if you remember, before what we did is we took the input, we segmented it, each block got a segment, Each block did a scan of its segment, and it produced partial sums. Okay, we scanned the partial sums, and then each block added the corresponding partial sum to its elements. Well, what we can do is within each block, we can also do a segmented scan. So if we zoom into one of these blocks, we can also do a segmented scan. So if this is the segment that the thread block is responsible for, what we can do is we can have each thread in the block take a subsegment of this segment. The thread scans its subsegment. Okay. Each thread places its value in another array. The thread block does a scan of this array of these thread partial sums in parallel. We've already seen how the thread block can do a scan in parallel. Okay, and then each thread is going to take the partial sum that corresponds to it, and it's going to add it to its elements. And then we produce the final scanned result for the entire thread block. Okay. So just like we use segmented scan to segment the input and divide across many blocks, we can use segmented scan to divide the block segment across many threads and have the threads do a sequential partial scan in order for us to improve the work efficiency of the algorithm. Is this clear to everyone? Would you guys like to implement this? All right, let's give it a try and see what this would look like. Let's go back to our code. I'm going to implement it in the context of the Kogistone, but it's the same thing whether we use Kogistone or Brent-Kung. Okay. So here, remember our time was 4 milliseconds, and let's see how much improvement we can get if we apply coarsening to improve the work efficiency of our code. So the first thing I'm going to do is I'm going to define a coarsening factor. So I'm going to call it coarse factor, and let's set it to 8, for example. So every thread is going to take 8 elements, scan them sequentially, produce a partial sum for those 8 elements, and then we're going to scan those partial sums in parallel. Okay. So let's get started. The first thing we need to do is we need to identify the segment that the thread block is responsible for. So this time, and there's going to be 2 notions of segment. There's going to be a block segment, and there's going to be the thread segment. So I'm going to call this the B segment. Okay. So the thread block is going to be responsible for. Remember, this is Kogistone. So if I have block dim threads, then without coarsening, I'm going to have block dim elements in the block. So with coarsening, how many elements am I going to have per block? So when each thread took 1 element, I had block dim elements. When each thread is going to take 8 elements, I'm going to have block dim times 8 elements. Or in general, I'm going to have block dim times coarsening factor elements per block. Okay, so to find out where the block segment starts, I'm going to multiply block dim times coarsening factor by the block index. Okay, so now every thread block has 1024 elements, and every thread block is going to take 1024 times 8. Sorry, every thread block has 1024 threads, so every thread block is going to take 1024 times 8 elements. Okay, so block 0 is going to start at 0, block 1 is going to start at 8 times 1024, block 2 is going to start at 16 times 1024, etc. All right, now that I know where the block segment starts, the next thing I want to do is I want to load the entire block segment into shared memory. Okay, so to do that, I'm going to have to create a shared memory buffer. I'm going to call it buffer underscore s. Okay, and I'm going to need to load the whole block segment. So how big is the shared memory buffer going to be? Well, every thread block, we said, is going to be responsible for block dim times coarsening factor elements. So the size of the shared memory buffer is going to be block dim times coarsening factor. Okay, now that I've declared this buffer, what I want to do is I want to load this entire buffer into shared memory. Okay. Now, what's the best way to do this? Should I have thread 0 load these elements, and thread 1 load these elements, and thread 2 load these elements? Is this the best way to do it?
No.
Or is there a better way?
The thread 0 loads element at position 0, and then 0 plus block dim times 1 plus block dim times 2.
Right, exactly. So I want thread 0 to all the threads to load the first part, then all the threads to load the second part, all the threads to load the third part, etc. Because I don't necessarily want each thread to load the elements it's responsible for, because that won't have good coalescing behavior. Okay. So what I want to do is I want to load. I have 8 subsegments in my segment. Okay, and I'm going to load them one at a time. So I will have a loop for unsigned int c equals 0. C is less than the coarsening factor plus c. Okay, and then buffer underscore s of and again, every thread is going to load. When c is 0, every thread is going to load the element corresponding to its index. When c is 1, every thread is going to load at block dim plus its index. When c is 2, every thread is going to load at 2 times block dim plus its index in general. And if we're going to have c times block dim plus thread index.x, and the value that it loads from the input is going to start at the block segment in the input, and then plus c times block dim plus thread index.x. Okay, so here what we've done is we've loaded the 8 segments in the block in a coalesced manner. Okay, next we're going to sync threads to make sure that we've loaded the entire block segment before we proceed to processing it. Okay, now that we've done this, the next step is for each thread to scan its own segment. All right, so now we're going to do the thread scan. Okay, and to do that, I'm first going to find each thread segment. So I'm going to call that each thread segment within buffer underscore s. Okay, so I'm going to call that t segment. So unsigned int t segment. A t segment is going to point to the segment of the thread within buffer underscore s. Okay, so what's that going to be? Well, it's going to be every thread is going to have how many elements? Every thread has 8 elements, right? So then it's going to be the coarsening factor times thread index.x. Okay. After finding out the beginning of the thread segment, we're going to loop through the element that the thread is responsible for and perform a scan. Okay, so we're going to loop over the elements. We have coarse factor elements. We're going to do unsigned int c equals, and we're going to start at 1. You'll see why. C is less than the coarsening factor, and plus c. Okay, and then we're going to do the scan. How do we do the scan? Well, buffer underscore s of, we go to the thread segment, okay, and we add c, okay, is equal to buffer underscore s of the thread segment plus c minus 1. Okay, the reason we start at 1 is because the first element in the inclusive scan array is just the element itself. Okay, so we don't need to do anything. But when we do the sequential scan, the second element, we add to it the first element. Now the second element becomes the sum of the first 2 elements. And then the third element, we add to it the second element, which was for sum of the first 2 elements. So now the third element becomes the sum of the 3, etc. Okay, so this is basically a sequential scan. And remember, sequential scan is work efficient. Okay, so for c equals 1, c is less than coarse factor plus c. Buffer of t segment plus c is equal to buffer of t segment plus c minus 1. So now when we're done with this, every thread is done scanning its own segment. Okay. The next part is for each thread to put the sum of all the elements inside of its segment in some array where the thread block will do the scan of the partial sums in parallel. Well, we've already written the code to do a thread block wide partial sum in parallel. That's the code down here. Okay, so then all that we have to do is over here in this in buffer over here. Remember, this is the Koji-Stone approach that was doing double buffering. So the first thing we were doing is we were initializing the buffer. Rather than loading from global memory, we already loaded from global memory. So what we're going to do is we're simply going to put in this buffer that we're scanning in parallel, we're going to put the partial sum of the thread block of the thread. Okay, so the partial sum of the thread is going to be the last element in the thread segment. So it's going to be at buffer underscore s of the thread segment. Okay, but we're going to look for the last element in the thread segment. So that's going to be plus the size of the segment, which is course factor minus 1. Okay. Clear to everyone? Okay, so then after we've placed the threads inside of the this array, the thread block is going to do the partial sum in parallel. So now each the block is going to do its own scan, and then it's going to give us the scan buffer underscore s. So here, this in buffer is going to get scanned by the thread block in parallel using this code that we wrote before. And at the very end over here, we're going to have in buffer underscore s is going to have the scanned partial sums of the threads segments. So after we've finished this partial sum, now each thread is going to take the corresponding partial sum and add it to its own threads. Well, it's going to take the partial sum for the previous blocks, for the previous threads, and add it to all of its own elements. Okay, now obviously the first thread doesn't have to do any addition because these results are already complete. Okay, so what do we do? We're going to write if thread index.x is greater than 0. So the first thread is not going to do a scan, is not going to do any addition. Okay, each thread is going to loop over its elements and add to them the result of the scanned partial sums. Okay, so how do I loop over the elements of a thread segment? Well, we just loop over we have a coarsening loop. So we're going to do unsigned int c equals 0. C is less than the coarsening factor plus c. Okay, and then each thread, so buffer underscore s of t segment plus c. So for each thread, for each element that the thread is responsible for, it's going to add the partial sum of the previous threads. It's going to add the partial sum of the previous threads. Where are the partial sums of the threads? Sorry, this is not supposed to be. Oh no, sorry, this is buffer underscore s. The partial sum of the threads are inside of in buffer. Okay, because this is where because in buffer was produced by the block parallel scan. Okay, so here we're going to do in buffer underscore s of thread index dot x minus 1, right? Because thread 1 is going to add the sum of thread 0, the elements in thread 0. Thread 2 is going to add the sum of the elements in thread 0 and thread 1, okay, which are going to be in the scanned array. It's going to be this value here. Thread 3 is going to add the elements, wants to add the elements in thread 0, 1, and 2, which in the scanned array, it's going to be the result at index 2. Okay, so we're going to do buffer of t segment plus c. We're going to add to it in buffer of thread index.x minus 1. Okay, of course, we're going to put the partial sum of the entire thread block so that that gets scanned separately. And then finally, when we store the result of the output, just like at the very beginning over here, every thread loaded multiple input elements. Okay, now every thread is going to have to store multiple output elements. So here, we're going to need to have 4. Of course, we need to sync threads over here, by the way, because we need to make sure that all the threads have updated their buffer underscore s. So we're going to need to sync threads. Okay, and then we're going to loop over the outputs for unsigned int c equals 0. C is less than the worsening factor plus c. And then the output of the blocks segment plus c times the block dim plus thread index.x, right? So this is the same index that we used when we were loading the inputs, right? So the block segment plus c times block dim plus thread index.x, okay, is equal to, and in this case, I'm going to use the shared memory buffer for the entire block segment, which is buffer underscore s now, and I'm going to index it with c times block dim plus thread index.x. Okay, so with that, what we've done is we've implemented the coarsened version of scan. Okay.
Professor,
Now, yes, question.
At some point, maybe there's a mistake. I'm not sure. When you place back the part in the partial sum, you're using in buffer, but shouldn't you be using buffer?
This is fine. You can do either. The reason is that the sum of the result of adding this value to the last value here, well, the last value here is this value here, right? The last value in thread 3 is this value over here. So the result of adding this value to the last value here is the same as this value here.
Oh, right. Okay. Yeah, sorry.
So the last element in buffer, which is this array, is the same as the last element in buffer underscore s, which is this whole array.
I see. Okay, thank you.
So yes, I could have used buffer underscore s over here. Either is fine. Okay, so then a few more things to take care of. In my add kernel, I'm going to coarsen that as well, just so that I have the same correspondence between blocks. So here I'm going to define again a block segment. So I'm going to have unsigned int b segment is equal to block dim times coarse factor, which is the number of elements that are responsible for, times block index.x. And then similarly, I'm going to have a loop. Let me just copy it for the sake of time. Okay, I'm going to have a loop over here, and then in every iteration, the thread is going to take the element it's responsible for, which is b segment plus same thing as times block dim plus thread index.x, and it's going to add to it the partial sums from the previous thread block. Okay, and then finally, I applied coarsening. I need to launch fewer blocks, right? So then I'm going to go all the way down here. I'm defining the number of elements per block, and rather than the number of elements per block being num threads per block, it's going to be num threads per block times the coarsening factor. Okay. So with that, thank you for being patient and waiting for the whole implementation of coarsening to complete. So having said that, let's compile, and now let's run it. And remember, before we had 4 milliseconds, and now, oh, we have a mismatch. Okay. So there must be a bug somewhere. 1 second, let me figure out what the bug is. Okay, so here we're back in the code. And basically the problem was that over here when we were doing the thread scan, rather than doing buffer of t segment plus c plus equals buffer of t segment plus c minus 1, I just did equals over here. So this was the problem. This was supposed to be a plus equals.
The screen is frozen. We can't see anything.
Okay, sorry about that.
It's fine.
Okay, so I'm back in the code over here, and the main problem, the reason behind the bug was that over here, rather than having plus equals, I just had an equal sign. So this is the part that was doing the thread scan, where the thread was doing a sequential scan of its own segment. So this was supposed to be plus equals. So every thread is going to add the previous accumulation to the current value. Okay, so let's compile this, and now let's run it and see the time. And as you can tell, before we were at around 4.5 milliseconds, and now we're at around 1.5 milliseconds from applying thread coarsening. So our code is almost 3 times faster than it was without coarsening. Okay. So this over here is the code that we just wrote, and you can read about what we talked about today in chapter 8 of the textbook. And that is all for today. Does anybody have any final questions before I finish? Okay, if not, then that's all for today, and I'll see you next time. Bye, everyone.
Thank you, Professor.